All right, this is our last lesson in probability in Algebra 2. We're going to be talking about binomial probabilities. We have a definition of what binomial probabilities are to start off here. Suppose you have repeated independent trials, each with a probability of success p. So before I go any further, that would be something like, just a real simple example, rolling a die. Every time you roll a die, that would be a new trial. And then the probability of success would be the same every time you roll that die. Let's say you were trying to roll a certain number like a 5. The probability of rolling a 5 each time is 1/6. That would be that probability p. Okay, so every time you'd roll, that's a trial. And then the probability of getting what you want, that would be considered a success. We call that P. The probability of failure we would call Q, and P plus Q would be 1. So if we were rolling a die, the probability of getting a 5, let's say that's what we wanted, would be 1/6, and the probability of not getting a 5 then would be 5/6, and those add to 1. You're looking for a certain number of successes in these trials. So we're looking for this number of x successes, and we're going to call the total number of trials n. This is how you would calculate the probability of getting x successes in n trials. It's going to look a little funny at first with all the stuff going on here. We need to make this calculation first. It's called n choose x, and it's using something called combinations, which we'll talk a little bit more about in a future section. Right now we're just going to use it to find the number of ways that we can have successes in our trials. We're going to multiply that by the probability of a success taken to the number of successes. And we're going to multiply that by the probability of a failure taken to the number of failures. And that is found by taking n minus x. So it's kind of tight here, but I'm going to write those things in here. This tells us the number of ways to get x successes in n trials. This is the probability of a success, and this is the number of successes. Q is the probability of failure, or not getting what you want. And then this n minus x, since n is the total number of trials and x is the number of successes, n minus x is the number of failures. That is a very complicated looking formula. We're going to try to break it down here, make a little bit more sense. All this stuff is kind of in this box right here. We're going to put some things there in a second, but I'm going to show you a little example here of what we're talking about. Let's say we want to find the probability of rolling exactly 4 3s in 10 rolls of a die. So I've got 10 rolls of a die just kind of right there. All right, and then I've already said here, let's show just one example. Here's getting those 4 3s. Okay, where you see the green 3s, those are getting the 3s. That's a success. And then all the other spaces we did not get a 3. So the probability of getting this failure here would be, oops, let's fill out this first. P would be the probability of getting what we want, which is a 3. Well, there's a 1/6 probability of getting a 3. So the probability of getting each one of these 3s here is 1/6 because it's independent. That doesn't change every time you roll the die. These are all 1/6. The probability of not getting a 3 is 5/6. So the probability here of not getting a 3 is 5/6, and it is every single time we don't get a 3 throughout that entire event. So what we have here is the probability of not getting a 3 and then the probability of getting a 3. So each time we're going to be multiplying these because these are all independent. And we said the probability, to find the probability of A and B, if they're independent, you just multiply them together. So we're multiplying all of those things together. So what you see here is that 1/6 is being taken to, or is showing up here as a factor 1, 2, 3, 4 times And the 5/6 is showing up as a factor the number of times that we fail, which is 6 times. So here we see like a good chunk of that formula. Here we see the p to the x, and we see the q to the n minus x. But what we're missing here is the fact that this is only one scenario. This is getting 4 3s in just those 4 spots out of the 10. There's all sorts of different ways that you can move those 1/6 around through those 10 trials. So to find out how many ways that can happen, we multiply that by 10, choose 4. We multiply that to that product that we already have. That'll tell us how many different ways that can happen. And I'll show you how to do that in your calculator here real quick. This is how you find combinations on your calculator. What I'm going to do is, I'm going to just go grab it first. We want to go to Math. This is under that probability menu where we were getting that random number generator before. Okay, so you see all this fun stuff here. What we want is NCR, so you want number 3. So I'm just going to find out what that value is, that 10 choose 4, and hit enter. So 210. This is one scenario out of 210 ways that those 1/6 could be moved around in that scenario. So we have 210 times, and then we'll take the 1/6 to the 4th and the 5/6 to the 6th to calculate the rest of it. So I'm not going to do each one of those individually. I'm just going to rewrite that right here. I just wanted you to have an understanding of what the 10 choose 4 was doing for us. So there's the 5/6 to the 6. And then I would just put this all into my calculator at once. So I'm going to pretend that I didn't calculate that 10 choose 4 already. And I'm just going to type this all in together. So I'm going to go back to that math, probability, math. I want number 3. I want that n choose r, so I'm going to go 10 choose 4. And then I'm going to just put this all in together here. I got 1/6 taken to the 4th, and then 5/6 taken to the 6th. And you could put the multiplication in there, but it knows that you want to multiply those things together. So when I hit enter, there's the probability of getting exactly 4 6s, or I'm sorry, what were we rolling to get? 3s. Okay. In those 10 trials would be 0.0543. We'll just round that to the 10,000ths there. Okay, so that would be the probability of getting those 4 3s, and obviously it wouldn't matter what digit you were going for on the die, it would be the same probability. But that is the general setup here. So let's come back here and finish filling this thing out again. I'm going to have you kind of write that out again, and choose x, and then p times p to the x times q to the n minus x. And then we're going to come back to this in a little bit. There are some other ways you can do it on your calculator too, but I want to show you how to do it by typing that all in. All right, so here's some important things. These need to be repeated independent trials. You can only have 2 outcomes, okay, and we consider them to be a success and a failure. And then the probability of success must remain constant for each trial. This is considered to be a binomial experiment, okay, when we're performing this, and then we can calculate the probability using that formula we just set up. So let's see if we can figure this one out. Probability of getting exactly 3 2s in 10 trials, or rolls of a fair die. Well, so what we changed here is now we're only looking to get 3 successes. So we know that our number of trials is 10. Our number of successes we're looking to get is 3, and the probability, or the getting a success is getting a 2 in this case. And our probability of success is again 1/6. Probability of getting a 2 when you roll a die is 1/6. So that means that Q is 5/6. Okay, so the setup of this then would be 10 choose 3 times 1/6 to the, this time we are looking for 3 successes. So notice that this number and this number are always the same. And then 5/6. These better always add up to 1 because these probabilities are complements. And then to get the number of failures, you just subtract the number of trials, or you take the number of trials and subtract the number of successes. So that's going to be 7. If I succeed 7 times, I'm going to fail 5, excuse me, slow down here. If I succeed 3 times, I'm going to fail 7 times. So we could type this in the same way that we did, but I want to show you another way to put this in your calculator as well. It's using this function called a binomial distribution. And we're looking for an exact and equals here. So we're going to do binom PDF on our calculator, it's called. And I'll show you where to find that in a second. Into the binomial PDF, we need to put 3 things: the number of trials, the probability, and the number of successes. Okay? So you could just type it in like this. That'll give you your answer. And I think for these types of problems, that's a legitimate way to go. It's almost as fast to do that as what I'm about to show you. Here's how you get to the binomial PDF. You have to go, and you might want to write this down. You might want to, or I'm sorry, get this from the distribution menu. Okay, the distribution menu is right above the variables button. So you want to hit second vars. And this takes you to all these fun distributions here. We want the one called binomial PDF if we're looking for an exact. There it is right there. Went past it. There it is. We want to hit enter on that one. So I'm going to type in 10 for the number of trials. And if you have an old calculator, you're going to be typing in like that, like I have written down there. And then the probability of success was 1/6. And then the number of successes we're looking for here is, I can't remember how many successes. I think it was 3. Okay, and then I'm going to hit enter. If you have an old calculator, you would have just typed it in just like that. So when I hit enter, that's going to give me my probability there. 0.1550. Doesn't really say what's round to, so we'll just stop there. Okay, we're about 15.5%. There's a 15.5% of getting exactly 3 2s when you roll a die 10 times. And just to show you that we could have typed that in the first way that I showed you, we'll do that again real quick here too. I'll go back up and just grab this guy and change the values. Okay, this time I was going to fail 7 times, or not get that value I wanted 7 times. I was going to succeed 3 times. Notice my probabilities stay the same, so I'm not going to change those. I need to change this to a 3 right here as well. And if I hit enter instead of hitting 3, isn't that a fun thing? So never mind what I just did. All right, probably would have just been faster for me to type it in from scratch. All right, so what we are going to try to change is that 4 to a 3 right there before we hit enter this time. I should get the exact same value there as I did when I calculated it using the binomial PDF. So they do the same thing, it's just 2 different ways of typing it in. Even if you are using the binomial PDF, we still would like you to write that down on your paper, because you're showing that you understand it's a binomial distribution and how it's built. All right, so now we're going to do a couple of examples using that process. This first one is actually a good one for us to review what a tree diagram will do for us. So take a second to read through that example and what's going on here. It says a fast food restaurant is attaching prize cards to every one of its soft drink cups. The restaurant awards free drinks as prizes on 3 out of 4 cards. Suppose you have 3 cards. Find the probability that exactly one of the cards will reveal a prize. So you have 3 cards in your hand. That's our total number of trials then. All right? We are looking for the probability that exactly one of these cards will reveal a prize. Well, that's our number of successes, and our number of successes is 1. The probability of getting a card that will get us a free soft drink is 3/4 or 0.75, because 3 out of 4 cards are winners. All right, so it's pretty much everything that we need to know to answer this question. We're just going to use a tree diagram to show you that it's a legitimate way to do this as well. So I got P for getting a prize and N for not getting a prize. So on the first card, I could get a prize or I could not get a prize with those probabilities. After the first card, those probabilities stay the same. I could get a prize or not get a prize on the second card. I could get a prize or not get a prize on the second card. Okay, so this, is my third card here. Those probabilities stay the same. All right. So these are all 0.75s and 0.25s. 0.75. If I can zoom in there a little bit. Hey, that's a lot nicer. Okay. Is this the best way to do this problem? Maybe not, but just to use our formula would work just fine, but I want to show you how the tree diagrams connect to this as well. So here's what we're looking for. We're looking for getting one winning card. So let's think about where that happens. How many winning cards are we looking to get? I'm sorry. Find the probability that exactly one of these cards will reveal a prize. You know what? I think that's kind of boring. I'll change that up. I'm going to make that 2. I'm going to say I want to win 2 soft drinks. Me and my friend both want to win a free soft drink. So what's the probability of, out of those 3 cards, that 2 of them are winners? Make this a little bit more interesting. So let's see how many of these scenarios have 2 winning cards. As I go through here, it would have to be, there's a prize, and then going along that oops, went the wrong way there. So there's 2 prizes, but then I wouldn't win one on the third. Then the other one going in that direction would be, there's 2 prizes, but then not winning a third. So what I have to do is calculate all of these probabilities by multiplying, like we did in the last section, to find those end probabilities right there. We'll find those out at the end by actually using the formula. And then on this bottom scenario, if I don't win one the first time, I have to win it in the next 2 cards. So this is the only scenario that could happen. So we have those 3 things going on there. There's 3 scenarios in which 2 of the cards are winners. In each of those scenarios, we'd have to take 0.75 squared because it's happening twice, and then the 0.25 is happening once because there's one failure. So that's happening on each of those, along each of those branches that I just highlighted. We also just said there's 3 different ways that happens. Well, if we did 3 choose 1, that ends up being 3, which is why we have the 3 branches there. And then we could take 0.75 squared times 0.25 squared, or to the first. Okay, and this is going to end up giving us that probability. So this is one way to set this up, by actually, well, you could leave this as a 3 choose 1, but this is one way to set this up to get your answer. You type that in, you'd actually get a 0.4219, or you could go binomial PDF. You could type this in your calculator and go, there are 3 trials. Probability of success is 0.75, and I changed the problem to have 2 successes. That would be about 0.4219. You could type it in either way. But you can see it visually in that tree diagram right there. All right, in the next problem, it says Alicia walks to school with her friend Juana. Juana's on time 80% of the time. So we're going to let arriving on time be a success. We're going to let X be that variable arriving on time. So we are looking for the probability in part A that we're going to be on time 5 days in a row this week. In other words, each day throughout the week is a trial. So there's a total of 5 trials here. So I'm just going to write n equals 5 here. For all of these, n equals 5. 5 days in the school week here. So we're looking for the probability that we are on time every day. So that's going to be 5 trials, 5 successes. Well, if you think about how many ways that can happen, that's going to end up being 1. There's only one way that you can have all your trials be successes, and that's to have them all be successes. So 5 choose 5 is actually going to be a 1. Okay, if you don't trust me, you can go ahead and calculate that on your calculator. 0.8 to the 5th, because we're succeeding 0.5 5 times, and then the probability of not being on time is 0.2. So I'll just come up here and just say P equals 0.8, which means Q equals 0.2. And that is going to be taken to the 0. Well, what's interesting here is 5 choose 5 is just 1. So we have 1 times 0.8 to the 5th. 0.2 to the 0, that is also just 1. So really this is just 0.8 to the 5th. So if we type in 0.8 to the 5th, and if you do a little thinking like that, you have a lot less typing to do in your calculator. Make this, I'm going to put this over here, n equals 5. If you do that thinking beforehand, you have a lot less to type in your calculator. So you get 0.32768 as our probability there. Okay, so what I'm saying is typing 0.8 to the 5th and was a lot faster than going through and typing 5 choose 5 and all that kind of stuff, because you should know that that's 1 and that's 1. All right, now we're going to look for the probability that she is on time 3 out of the 5 days. So 3 out of the 5 days, we're looking for the probability that now x is 3. So now we have 5 choose 3, 0.8 to the 3rd, 0.2, we're going to be late 2 days. And this one we can go ahead and type in. So I'm going to just use my 0.8 to the 3rd and 0.2 to the 2nd. And this is going to give us about 0.2048. Okay, if we would use the binomial PDF, I'll just show that one more time here. We got to go second distribution, and then we want that binomial PDF distribution, which is part A right there. Or not part A, it's just letter A. So this time we have 5 trials. Probability of a success is 0.8. And then we were looking for exactly 3. I can keep that the same. I should get that same 0.2048. All right, what is the probability that she is on time at most 3 out of the 5 days? All right, so let's see here. At most 3 would mean that she was on time 0, 1, 2, or 3 times. So that would be that x is less than or equal to 3. All right, so you'd have to add up 4 different probabilities here. I'm just going to say all the way from the probability of 0, that you're on time 0 days, all the way up to the probability that you're on time 3 days. That'd be 4 different probabilities that you'd have to calculate there. Okay, and so you'd have a lot of stuff to type in your calculator. So I'm going to show you a little trick for doing this. The complement to being on time at most 3 of the days would be that she's on time, that you're on time 4 or 5 of the days. So we're going to find that. So that would only have me calculating 2 probabilities using the binomial PDF. But I got another little trick for you here too. We're going to use binom CDF this time. Okay, and I'll explain to you what that is. Okay, before I finish this problem, let's come up here and look at this thing, this CDF. If you're looking for the probability that you are less than something, okay, and actually this should be less than or equal to that value. You make sure you change that. Then you want to use binomial CDF. And what this will do, you put the same information in, but what it does is it finds a probability, the cumulative probability, the C stands for cumulative, which means it adds up all the probabilities from 0 all the way up to the probability of whatever value you put in for X. All right, so if I want to find the probability of oh, and actually this is going to be a lot easier. Sorry, I thought we were doing this the other way. That is what we're looking for. So we can do. Let's scratch this for a second. I'm sorry about that. That's what we're looking for. When you're looking for from 0 to 3, that is a cumulative right there. So this is what we want to use. We want to use the binomial CDF again, like I was trying to set up. But out of those 5 trials, if we use CDF here, it's going to go from 0. It's going to actually, I don't have to write it over again. It's going to do that. If we put the C instead of the P there. So we're going to go 5. Probability of being on time is 0.8. And then the probability of or the number of successes that we're looking to go up to is 3. Okay, so by putting the C there and by putting the 3 there, it's going to find probabilities of 0 through 3. So when we type this in, and we go back to that distribution menu, go back to where we were before. This time we don't want the PDF, we want this one, we want the CDF. Okay, so now it looks exactly the same, but that's a huge difference with the C right there, because now it's going to be adding all the probabilities from 0 to whatever you put right there. So we've got 5 trials again, still a probability of 0.8, and then this time we're going to put that 3 right there. So really, I think I had the same stuff in there as before, but it's going to give me a different answer because it's going to add from 0 up to 3. We're going to get about 26.3% here. Or 0.2627, whatever you want to round to there. So when you want to go from 0 to a number, or in other words, when you're told at most, you want to just use the CDF. What I was starting to set up there on accident was when you're asked at least something, then we're going to want to subtract that from 1. We'll see that in an upcoming example, but I'm going to have to do that in a different video. Actually, I think this is still recording, so I'm going to just keep going and just finish this up with what I got. All right, so on the next page here, we're finding, they just are giving us the values we need to put in. What's important here is whether or not we're looking for an exact number of successes like there, or if you're looking for a couple of different probabilities you have to add together like we are in the second one. So in this first one here, we're just looking for probability of 2 successes. And our number of trials is 5, so I'm going to go 5, choose 2. Probability of success is 0.25. I'm going to have 2 successes. Probability of failure is 0.75. If I have 5 trials and I succeed twice, I'm going to fail 3 times. Okay, and I'm not even going to worry about doing the binomial PDF on this one. I think you should just type it in like this whenever you can. I think it's just as easy. So we're going to go math over the probability. Number 3, 5, choose 2, and then get out of there. 0.25 taken to the second, and then 0.75 taken to the third. Or like, you could use binomial PDF. There's nothing wrong with it. Just round to the 10,000ths there. Okay, or you could give it as a percentage. That'd be fine too. All right. So this one, x is greater than or equal to 8, is the same thing as saying at least. And when it says at least, you usually want to just do 1 minus the probability that should be less than or equal to the number that's below it. Because this is what you can calculate using the binomial CDF. All right, so this gets a little confusing because that doesn't have the 8 in it. All right, but if the way that I look at it is, these are the different things that could happen. How many trials we have here? We have 10 trials. Okay, so these are the different number of successes you could have if you had 10 trials, anywhere from 0 up to 10. Those are the, you could say those would be the number of successes. We are looking for the probability that x is less than, or I'm sorry, greater than or equal to 8. We're looking for that probability right there. This is what we want. Okay, but our CDF finds from 0 to something. So if we find this on our calculator, 10, probability of success in this problem is 0.7, and if we go up to the 7, we're finding what we don't want, right, when we calculate this. So we need to subtract that from 1. So I'm just going to say that probability that x is greater than or equal to 8 is equal to 1 minus the probability that x is less than or equal to 7, which means I can just do 1 minus the binomial CDF, which would go from 0 to 7, 10.77. All right. Now, if you wanted to, you could just calculate these 3 individual probabilities using binomial PDF or the formula and add them together. And you're going to get the same answer we're about to get. So we've got 1 minus binomial. Actually, let me do this first. Before I subtract it from 1, I'm just going to calculate what the probability is from 0 to 7. So you can see that. So I'm going to cheat. Actually, it's not cheating. This is just being smart about what you got on your screen. I'm going to grab this so I don't have to go find that, except it hits enter too many times. So we'll grab it again. Okay, and I'm just going to change these values to what I want them to be for this problem. So I want 10 trials, and then I have 0.7 as my probability of success, and I'm going to go up to 7 because of the CDF. Okay, but I hit enter. I just found that there's and for some reason it likes to do it twice, but I just found that this probability, the probability of getting 0 through 7 successes, will be 0.6172. Okay, that's probability of getting that stuff, those number of successes, all of them added together. I want the probability of those. So I'm going to subtract it from 1. So I'm just going to take 1 minus, let's say, second answer. So our answer is going to be 0.3828. So the probability of getting those guys of up to 7 would be 0.3828. And the probability of getting those guys, oops, sorry, got that backwards, 0.6172, and the probability of getting those guys would be 0.3828, and that's the one that we want. All right, so what we just did, I'm going to just put on here as our useful reminders here. 1 minus the probability of what we don't want is always going to give us the probability of what we want. And this is useful when you're doing problems like this one where it says at least. Okay, this is nice for the at least problem. So the probability at least something would be 1 minus the probability of what's up to it. Here's another nice thing to know. The probability of at least 1. Okay, and then I'm kind of doing the same thing with those, like, here's the number of things that could happen, like I just wrote up above. In 5 trials, the number of successes could be 0 through 5, right? Probability of at least 1 means 1 to 5. So what's really easy is to just find that probability and then subtract it from 1. So take 1 minus the probability of none if you're asked to find the probability of at least 1. So I'm just going to put this as none. and then this is at least 1, is what that means. Okay, now why is that easy? Because the probability of none is always just the probability of failing all trials for every single trial, so q to the n. Let's see if we can put that to use here. So this says if it rains, or when it rains, there's a 70% chance that the soccer practice is going to be canceled. If it rains for the next 3 days, so it's going to just rain all 3 days, what is the probability that the practice will be canceled at least one of the days? So our P is 0.7. We're talking about 3 days here, so N, our number of trials is 3 days. And we're looking for the probability that it's going to be canceled at least 1, so that X is greater than or equal to 1. All right, so now this is kind of strange because we're saying that canceling practice is a success because we're letting 0.7, that probability of soccer practice being canceled, be our probability of success, which, if you don't want to go to practice, I guess is true. So the probability of at least 1, we said, is easy to find by finding the probability of none, or that the practice is not canceled at all. So that would be 0.3, which is Q, taken to the third. Which is going to be about 0.973. And it says if it rains for 15 days straight, what is the probability that practice is going to be canceled at least 10 of the 15 days? All right, so now N is 15, and we're looking for the probability that X is at least, so greater than or equal to 10. So, and that doesn't mean, greater than 10 forever. It just means 10 through 15. So if you wanted to, you could actually calculate each of those probabilities. Probability of 10 practices being canceled, all the way up to probability of 15, which is only 6 probabilities, but that would take a long time to calculate. What we're going to do is use this idea of, well, let's find what we don't want, because that's what our calculator can calculate with the binomial CDF feature. So we've got the probability of X greater than or equal to 10 is equal to 1 minus the probability that X is less than or equal to 9. And that's nice because then we can just use our binomial CDF, because it'll go from 0 to 9. So I've got 15 days, 0.7, and we're going to go up to 9. If you go ahead and punch that in, you're going to get 0.7216. All right, this video is reaching the 40-minute mark, and I think that's a good time to stop then. And the nice thing is we aren't doing this sort of problem this year, so you don't have to worry about that last example.